Hello, welcome back. We have been discussing the first unit of applied physics, that is quantum mechanics. We'll discuss the particle in one-dimensional potential box in two parts. In this video, we'll discuss the definition, we'll set up the Schrodinger's equation, and we'll find out the eigenvalues. In quantum mechanics, those problems that can be solved exactly without using approximations are known as exactly solvable problems. One such exactly solvable problem is a particle in one-dimensional potential box. In this problem, we are going to find out the eigenvalues and eigenvectors. Mathematically speaking, the problem is a boundary value problem. Means it has certain boundaries. Look at the geometry closely. For all values x is less than 0, the potential is infinitely large. For 0 less than x and less than a, the potential is 0. And again for x greater than a, the potential is infinitely large, which means on either sides of 0 and a, we have infinitely large potentials. That makes the potential box. Since it is infinitely large, one can also call this as one-dimensional infinite potential well. In this potential well, we'll have a particle with mass m. This particle will possess certain kinetic energy. Since it is having kinetic energy, it will be oscillating between these two limits. We have boundaries. One is at x is equal to 0 and the other one is at x is equal to a. As a result, the particle will be oscillating between these two boundaries. Since the kinetic energy of the particle is small, the particle always lies close to the bottom of the potential well. Now we'll write the Schrodinger's equation. The equation will be d square psi of x upon dx square plus 2m upon h bar square e psi of x is equal to 0. We'll call this 1. In this equation, h bar is h by 2 pi and psi of x is the wave function we are trying to find out. Now we'll define a quantity k square, that is 2m e upon h bar square. So we are defining a quantity like this. K square is equal to 2m e upon h bar square. Using k square, one can write equation 1 as d square psi of x upon dx square plus k square psi of x is equal to 0. And this is a standard differential equation, and we know how to write the solutions for this differential equation. We'll call it 2. We shall try to write a solution that gives rise to oscillatory behavior for the wave function psi of x, because the particle is oscillating between the limits x is equal to 0 and x is equal to a. So we write psi of x is equal to a sine kx plus b cos kx. We'll call this 3. Now we look at the boundary conditions. Since the particle is confined to the region between 0 and a, the amplitude of the wave function at x is equal to 0 should be equal to 0, and at x is equal to a also should be equal to 0. Reason is the particle is having oscillatory behavior. So the boundary conditions are psi of x at x is equal to 0 is 0, and psi of x at x is equal to a also is 0. We'll apply the first boundary condition, that is psi of x at x is equal to 0 to the wave function. Then you write a sine k0 plus b cos k0. We know that this gives rise to cos 0. Cos 0 is equal to 1, which means the first term will be 0 because sine 0 is 0. 0 into a constant is again a 0 plus b. And what is the value of psi of x at x is equal to 0? That is equal to 0. So this will be equal to 0. This implies the constant b is 0. Now we'll try to find out constant a by applying the second boundary condition, that is psi of x at x is equal to a is equal to 0. So we'll apply that a sine ka is equal to 0. In this, a cannot be equal to 0 because if a is 0, b we have already found that it is 0. If a and b both are 0, then we'll arrive at a trivial solution where psi of x is 0. That is not the desired solution. So a cannot be equal to 0. Then the other term, that is psi ka, should be equal to 0. This implies ka should be equal to some integral multiples of pi or n pi. N can take values 1, 2, 3, so on and so forth. N is known as the quantum number. From this condition, we'll write the energy spectrum. We'll take square on either sides. K square a square is equal to n square pi square. This implies 2me a square upon h bar square is equal to n square pi square. From this, one can write E as n square pi square h bar square upon 2m a square. This can be written as En is equal to n square h square upon 8m a square. Here we are representing E with En, the reason being corresponding to each of n value, because we know that n can take values 1, 2, 3, 4, so on and so forth. Corresponding to each of those n values, we get different energy. We represent each of those energy levels with a suffix n. So E1 corresponds to the first quantum number, n is equal to 1. Then you get E1 is equal to h square upon 8m a square. Similarly, E2 will be 4h square upon 8m a square, or h square by 2m a square. E3 will be 9h square upon 8m a square. In general, En is equal to n square h square upon 8m a square. Here, En is known as the eigenvalues. Please note that eigenvalues are dependent on the width of the potential and mass of the particle. They are also dependent on the quantum number. If you try to plot the eigenvalues, one can get the eigenvalue spectrum as, we'll plot energy along the y direction. This is 0, and for E1, so much will be the energy. For E2, 4 times this much of energy. And for E3, it will be 9 times this much of energy. So this is what is called as eigenvalue spectrum. In this video, we have said that we are going to write the Schrödinger's equation, definition of the problem, and we are going to find out the eigenvalues. We have said initially that it is a boundary value problem. When you look at the geometry of the problem, we know that there are two boundaries. One boundary between a region with v of x is equal to infinity and v of x is equal to 0 at x is equal to 0. The other boundary is at x is equal to a, separating v of x is equal to 0 and v of x is equal to infinity. We have written the Schrödinger's equation as d square psi of x by dx square plus 2me psi of x upon h bar square is equal to 0, where h bar is equal to h by 2 pi. We have defined a quantity k square as 2me upon h bar square. Using k square, we have written the Schrödinger's equation in a known differential equation form. That is d square psi of x by dx square plus k square psi of x is equal to 0. And we have written a solution for the differential equation that has some oscillatory behavior. So we have written psi of x as a sin kx plus b cos kx, where a and b are arbitrary constants. We have obtained these constants by applying the boundary conditions that are psi of x at x is equal to 0 is 0 and psi of x at x is equal to a is 0. Applying the boundary condition psi of x at x is equal to 0 gives us b is equal to 0, and when you apply the boundary condition psi of x at x is equal to a is 0 will give us ka should be equal to n pi. We have said n can take values 1, 2, 3, so on and so forth, and these are known as quantum numbers. Upon taking square on either sides, k square a square will be equal to n square pi square. We have written en is equal to n square h square upon 8m a square. So for different values of n, we have written the energies and we have seen the energy spectrum. We have written the eigenvalues finally. En is equal to n square h square upon 8m a square. In the next video, we shall write the eigenfunctions. Thank you.